It's a great pleasure to be here. Thanks very much for the invitation. And yeah, so my name is Philipp Haller. I'm an associate professor at KTH, and I work on, yeah, programming languages, concurrent programming, type systems, things like that. And most of my work is sort of in the context of Scala. So yeah, and today is about concurrent programming. So maybe just a quick show of hands. Who of you is using, say, futures in Scala on a regular basis? Okay, thank you. So that would be, I guess, between 20 and 30%. Okay, but then at least you guys will be well prepared. For the rest, I hope it will be, reasonably understandable. Because I'm going to start with an example here. So what we have here is, let's say we're given a list of future of int, right? So just a list of futures, and each of the futures will, compute in integer, okay? And so we have a bunch of futures, right? And we want to convert this to a single future of a list of ints, right? And so the idea is that, when all of these futures in the list have completed, this resulting future, this single one, should be completed with the list of all the results. Is that clear? Right? So this is a pretty simple problem. And how would we want to, how could we try to solve this? Well, okay, so let's start with, our list of futures, right? And I'm just going to populate this, in some simple way. So that will give us, list of 10 futures, and they all compute in integer. Fine. And now what we want here is, a single future that will be completed with the list of all the results, right? And well, how could we try to solve this? Well, we could, create a future because we want to have a future, right? So we can create a future, and then we can say, well, we just take our list here, our list of futures, right? And, for each future in that list, we would like to wait until it's complete and then kind of return the result, right? That would turn a list of futures into a list of ints, right? Because we just convert each future into an integer, right? We just need to figure out how we can await the completion of the future, right? And is that clear? Right, so we just use map on a normal Scala list, and for each future we want to wait for the integer result and have that as the result here in the map, right? And so that will give us as a result a list of integers, right? And that's going to be wrapped in a future. So that should give us the correct result. And now I can look at the future API, and there are various methods, and that we can use to respond to the completion. So we could try to check out this onComplete method. Now the problem is that onComplete, we need to register an event handler which gets invoked once the future completes, but it doesn't actually return the result, right? onComplete has return type unit, so it doesn't solve the problem. So this is certainly not a solution, right? So now you could think, well, okay, future map, I don't know, is that possible? Well, that will just create another future, right? So it, again, does not let us, give us the result. So this doesn't work either. And then if you look a bit further through the entire API, we can find, okay, there is actually an object await that has a method result, where we can actually wait for the result of future, and the result method returns that result, okay? And well, we have to give some timeout here, so okay, we provide something, right? Okay, I mean, this will work actually, so this compiles and runs, right? And but there's a small issue here, which is not so nice, which is that this awaited result call, it blocks the calling thread, okay? So the issue is, futures are multiplexed onto a thread pool usually, right? So we have let's say if you run on like a 8-core machine, you will have a thread pool with 8 threads. And if you create 100 futures, they will all be multiplexed to this thread pool. The issue is that, if we call result, enough times, we might block all these threads in the thread pool. So this is not really the best way to do it. So the best case scenario is actually that the thread pool, or in Scala parlance, the execution context, supports something called managed blocking, in which case the thread pool will actually dynamically resize. So it will actually create another worker thread just in case it's needed, because we're blocking one of them, right? So it's actually safer if we create another thread, just in case. But this, of course, leads to some performance degradation, because if we have, lots of these await.result calls, we will just blow up the size of our thread pool. And each thread is really expensive because, it has a huge stack, multiple like megabytes of stack and so on. And so this will really, degrade performance. And the worst case scenario is that our execution context does not support this managed blocking that I mentioned. So if you want to know details, well, you find this in the documentation online on futures. But if we have an execution context, because they're exchangeable, right? If you have one that does not support this, then, well, the thread is simply blocked. And depending what the other threads are up to in the pool, this can really cause big issues, in worst case, some deadlock. So yeah, this is not the best solution. Should do something else. And well, what could we do instead? Someone knows, as a suggestion? Okay, someone mentions promises. Okay, yeah, maybe you might be able to do that. There's actually a simpler way. Oh, sorry. Before I mention the simple way, I'm just gonna explore another alternative, right? So for example, we could say, well, there's the Scala async library, for instance, which has a nice method, right? It's called await, where you provide a future of t and it returns a t. So this looks like ideal, right? So we could try to use that. The problem is that Scala async actually has a limitation which says that the await cannot be nested under a lambda, but that's exactly where we are, right? We're within this lambda. So we cannot call await at this point, and we cannot call it either if we would have like a local method or a class or something like that. So we can't actually use it. Okay. So then, of course, we could, explore the futures API a bit more, and we can find out that instead of using list.map, there's actually a method called sequence. Okay, so in the future object, there's a method sequence which takes a list of futures, and it will return a future which is completed with collection of the results of these futures when all of these have completed. So this is exactly what we want to do, right? We want that, once all of these futures have a result, this resulting future should be completed with a collection of their results. So this method is actually exactly what we need for our use case. Okay, I mean, we could be happy with that. And in fact, it's very well behaved. Asynchronous, non-blocking, and works for all kinds of collection types as well. So it's pretty good. But it's like a specialized method, essentially to deal with collections of futures. Now let's make the example slightly more complicated. So let's say we want to filter the elements as well. So the resulting collection, should only have integers less than 500. Yeah, it's just a filter. So how could we try to do that? Well, we could simply say, well, we again use our sequence method, right? But now we say, well, each future should be transformed into another future which in this case, has a result which is a list. And the list either contains a single element if this passes our filter, or it's an empty list. This is a quite convenient way to do it because then we have a nested list and we can just use flatten to get our result, right? So basically, even if the future does not pass our filter, it still is completed with a result, right? So we can still use sequence to wait for all the futures to have a result. And at the end, we just, flatten it so that the empty results are discarded, right? So this is, pretty convenient and is kind of reminiscent of like using flat map if you want to do, map plus a filter, right? With sequential collections, you could use flat map in a similar way, except here we need to, first transform each future, and then, use sequence. Okay. All right, so we could do that. But yeah, we have to use, more futures API, obviously, right? We cannot use methods of list. They're just out of the question there. Okay, but isn't there a simpler way, right? Because the problem that I pose is quite simple. But here we need to do quite some, relatively complicated, steps. So isn't there a simpler way, right? Because there are some issues actually with this code. And it really has to do with the fact that once you're in the future world, it's hard to break out of it, right? And this is true for essentially all monads. So, if you used Katz effect or Zio and so on, you're in a similar situation. So what I'm saying now, this applies also to such libraries, okay? So first of all, of course, await result, as I said, we cannot really use, or we shouldn't use because of either performance degradation or deadlock. And Scala async also doesn't work because it doesn't allow waiting from within a lambda. So what we end up doing is we need to really use all the methods in the futures API and combine them correctly to achieve what we want to do. But there is a kind of an issue because if you can't use any of the collection methods with concurrent code, that's a slight issue because collections provide hundreds of methods, right? So if you just look at list, for example, or map or whatever, like all the methods that they implement or inherit, it's hundreds of those. If you can't use any of them, we would have to duplicate all of them to work with our given monad, okay? So it's good if you're a creator of one of these monad-based frameworks because you have endless consulting jobs. But yeah, maybe there's a different way to do things. And the better way, I think, would actually be that we could just directly, create our result that we want. So if you want future of list of int, we just create a future. And now we just need to come up with a list of int. And how do we do it? Well, we can, for instance, call flat map on our list. Call flat map. For each future, we wait for its result. And then, based on the filter, based on the predicate, we return list of v or else an empty list, right? And that will give us, thanks to flat map, this will directly give us a list of ints, right? So, this is really cool. But of course, this only works if we can reuse flat map of list, right? That's what we use. We use flat map directly on list. So it requires us to have support for this kind of thing. Some kind of await, it can be used nested within a lambda, right? And in fact, it is possible to do that, even in a very nicely behaved fashion, where we don't block any underlying thread, okay? We just suspend the enclosing future, which in this case would be the one here, right? That we created here. So we just suspend, and then the next future is completed, and we continue, and we just do this for all the futures, right? And this is actually well behaved, because even if the first future takes a long time to complete, well, in the meantime, all the other futures may be complete. That's fine, which means that after a slow future is completed, we can direct the await for already completed futures will immediately return, right? So this behavior is actually really good, what we want. So, and the code is super simple, right? Now the question is, yeah, if we directly compare this, we see, this is quite a lot simpler, especially if we now switch to Scala 3 optional braces, right? So who of you has used this before? Couple of people, 4 or 5 people. Yeah, so I mean, bracelet or braceless syntax basically just means that instead of having the curly braces, we just write a colon and then we indent the code that follows, and that is the stuff that would go into the braces, right? So we can say future colon, so that, and then all the indented stuff goes into the block, and we can use it for closures as well. So here, we can write colon instead of, braces here and at the end of the indented code. So this is, yeah, pretty concise if you use this a little bit, and you get used to that. But you can see that this is much shorter than the previous code, right? So yeah, so this is quite neat. Now the question is, well, okay, what are some benefits? Okay, so I mean, yeah, one cool thing is we can use list.flatmap, so we don't need specialized methods for futures. Okay. In fact, we only need one API method here, await, right? Also, we don't need some intermediate nested list. We can just directly use flatmap, which is very convenient. And actually, what's also cool is that it's possible to statically enforce so-called effect safety. This is based on an experimental feature in Scala 3 called capabilities or capture checking. I will talk a bit more about this later, but this is an experimental feature still. It's not in a, it's hidden behind a flag and so on. But yeah, how is this possible? Well, actually, the code I showed you is written using a new, also experimental concurrency library called Gears. And it has some key features. One is that it's based on lightweight concurrency. What do we mean by that? Well, it means that the concurrent tasks, like futures, are super cheap. So in terms of memory consumption, context switching, they're very cheap. So it's, yeah, you can, it's like an AK actor. Let's say you can create lots of them and it will just work, right? You don't need to worry about how expensive they are, right? So that's cool. But what's more, and that's really novel, which is that they can always suspend. Like at any point in the execution of the code, they can suspend without blocking any underlying OS thread. So it's really amazing, right? You can just suspend them and resume, and that's it, right? And you're not blocking anyone. So this is really cool, and this actually requires some new technology, let's say, on the underlying runtime. So on the JVM, you need virtual threads from JDK 21. And on Scala Native, it's also supported based on so-called delimited continuations. Yeah, that's, I don't have time to explain what they are, but it's, yeah, it's essentially a way to have computations that you can suspend and resume almost arbitrarily. Scala.js currently there's no support for that, and that, yeah, has to do with the fact that there's no such equivalent yet there. Okay, but the second, so this was the first important feature, okay? The second important feature is that the effects that we do are represented using so-called capabilities, okay? And I'm gonna show you what this means. But the cool thing about this is that we have something called effect polymorphism. So we can use methods like list.map, list.flatmap, and so on. and they can take closures that have different effects. And well, I have a separate slide about what this means, but it's basically polymorphism enables a lot of code reuse. That's the bottom line. I will show you some examples later. But moreover, not only this, but later, again, it's possible to enforce so-called effect safety, which means that the compiler can check that whichever effects you have, they will be handled. So for example, you might know this from checked exceptions where, or like the goal is if you have an effect such as throwing an exception, right? Then the compiler can check, or in effect safety, the compiler would check that there is a try-catch which will definitely handle this exception. So that's what effect safety means. It means that whatever effect you do, it will be handled. And this will also be possible using an experimental feature that's called capture checking. Again, I will talk more about these things. So first, effects as capabilities. What does this mean, right? So first of all, when you do concurrent programming, there's lots of effects. So if you start concurrent computation, that's an effect. And it needs some resources like a thread pool and so on. And a context, right? For example, execution context is required. And in fact, in Scala 2, we've been doing this all the time, right? We have in these futures API, it's full of these implicit parameters that take, where we have an implicit execution context. And this is essentially the same thing. So in a sense, it's specifying that the method has a concurrency effect, basically, because it says that it requires this execution context. And but also, for example, suspending a computation to wait for the result of a future, that's also an effect, right? And you can also think of message passing, like sending and receiving. That could also be an effect that you might want to check, right? Like let's say so there's all these effects, and in this gears concurrency library, they are specified using context parameters. So which is what, in Scala 2 we used to call implicit parameters, right? So just like in Futures API, we have implicit execution context, and the exact same parameters will be used for the effect safety that I will show later. So for example, if you look at the gears library, the future, has, for example, a method await result, which is sort of a variant of await, which returns a try. So try can be successful or can be success or failure. But you see here that it has the using clause. So using is the implicit of Scala 3, right? In Scala 3, this was implicit was renamed to using in this context, right? But basically, it's an implicit parameter, which is an async context that's required if you want to, that's required for the suspension that the await has to do, right? So it's basically the async is the effect. So basically, the await result has an async effect because it has an async context parameter. And so you can only call, what this means here is that you can only call await result in a context where there is a given or implicit of type async in scope. Yeah, and I'll show you how to create one. And then if you look at future, so if you create a future, we have to provide a body, right? And the body here has a very interesting type. It's who knows what kind of type this is? It's called a context function type, okay? This is more advanced feature here. But basically what this means is that you can pass a closure as the body. So, typically you have, either curly braces or a colon, and the compiler will automatically add an implicit parameter of type spawn to that function. And this means that within the body, we can use that implicit, right? So in the body, we can call methods that require this in the using clause, right? Because, the compiler has created a function that takes the spawn as an implicit parameter. So that means within the body, it's available, actually. So just yeah, so let's have a look at an example. So code in blue is using gears. Code in green is what the type checker infers. And so what's happening is every gears program needs one of these async.blocking blocks, at least one. So typically this is like in your main program, right? And that one says, okay, we execute the body on the current thread. And if inside we have to wait, then the current thread will suspend, right? So at some point you need to have this kind of functionality, right? But the cool thing is that the body here is also a context function. So the compiler will automatically create this implicit parameter using spawn. And that means that inside the body here, we have this given of type spawn in the scope. And that means we're allowed to spawn a future, so create a new future. And spawn is a capability which also, has a wait, supports suspending. So we can also use a wait, for example. So this is quite nice. So then within this block, we can create new futures like this. And if you create a future, if you spawn a future, yeah, the body here, again, the compiler will, add this context parameter. And so within here, since spawn has both capability to spawn and also suspend, we can use a wait as well there. So we can directly call map on list, and within the lambda, doesn't matter, we can await, okay, because we can suspend at any point in time with this. Right, so this is pretty cool. So yeah, async blocking is actually the only way to get a spawn capability from the beginning. So you start with no capability, and then you need to create one at some point. So then this, you need to have at least one call to this thing so that the capability is created, and then later, of course, you can pass it on to other methods that need it, basically. Okay, now what is effect polymorphism? Because that's an important ingredient. So let's say we have a function of type int to int, right? Takes an int, returns an int. And let's say it has an effect, e, some effect. Could be doing IO or throwing an exception. It doesn't matter, right? It has an effect e. Now, what should be the effect of calling map and passing this function, right? What is the effect of this call to map? Anyone has a suggestion? So if fun has effect E, what should this, what effect should this call have? Okay, you say list of E. Okay, that's a possibility. Someone says E. Yes, that's also a good suggestion. Thank you. So yeah, I mean, basically, like you can think of it this way, right? So let's say E, it means throwing an exception, right? Throwing some specific exception. Well, if the effect means that it's possible for the function to throw the exception, then map of fun means it is also possible that this thing throws the exception. So normally what we say is that the effect should be E. Okay, so they have the same effect actually. But this means that the list.map method is actually polymorphic in the effect of its argument. So whichever effect fun has is the effect of map when we pass the function. Yes? Okay, thanks. Right? So this is what effect polymorphism means, okay? So now you can go around and tell people that you know what effect polymorphism is, and they will think you're super smart. But this is super useful because it means we can reuse list.map and so on. If you want to read more, here's a reference you can have a look at. We did this a while ago, actually, where we wrote a paper about this. But so how do capabilities support this? So in the experimental Scala 3 feature called capture checking, there's actually a new function type with a single arrow here, and that represents pure functions, okay? Hooray, Scala now has pure functions, right? So it's functions that are effect-free, right? Whereas if you have a double arrow, the one we know and love, well, it's potentially effectful, right? And now the higher order functions like map, they are effect polymorphic by default, right? So the map method of list, right? Actually, if you write it like this with a fat arrow, it means that, again, effect polymorphism. So it means the effect of map is exactly whatever the effect of the argument is. Okay? And the type system is designed so that the method type here does not need to change. This is by default, expresses effect polymorphism. Right? So that means, and that's why it's possible that we can pass a closure that has an async effect. For example, because we call await, right? If you call await, we have immediately the async effect. And it's possible to pass a closure with the effect because, well, it's effect polymorphic, and it just means that the map itself may have the async effect, right? Okay, that's it. But that means that, okay, when we call map, we also need the async capability in order to do that because it contains a closure that has the effect, right? So here, right, feud.await has the async effect, and so the closure has the async effect, and since map is effect polymorph, the call to map has the effect async. So that means you can only do that within a context where you have the async implicit in scope, basically. So where you have the async capability. All right. So now capture checking. So there's a final ingredient. So that's, like I said, an experimental language feature, but it's quite far along. So I think it'll soon be available. So in Gears, the idea would be, this is hypothetical because it has not been implemented yet, but the idea is that you could enforce the scoping rules that you need. So for example, let's say you take an async capability, right? Because a function takes the capability because it uses await, let's say. Well, this async capability, because it's just a context parameter, this should not be captured, right? This async parameter should not be captured in a way where its lifetime exceeds that of the function's body, right? Because then you could suspend in a different context where you don't really know what to do because you're not in an async context. So you need to restrict it, and with capture checking, it's possible to do that. In principle, like I said, it's not been implemented, but I'm sure it will be. Okay. So there's actually a nice tutorial on this capture checking, so highly recommended. Has some more examples, really cool. And there's also a research paper about this. So I'm actually not one of the co-authors, as you can see, but I still highly recommend this paper. Yeah. But yeah, what am I working on with my students and so on? Well, we've been working on data race freedom and how to enforce it. So there's different work that has been done, is ongoing and so on. So here also the question is how to support different concurrency models. So I just worked with a student on the async finish concurrency model that was introduced by the X10 experimental language from IBM Research a long time ago. But well, it's actually one of the pioneers of, let's say, structured concurrency. So it's quite interesting. Then we're also working on ownership and ownership transfer in Scala. So that's sort of Rust-like typing. And but we also have other topics like concurrent programming, deterministic concurrency, distributed programming. So we just completed some quite exciting work on proving the failure transparency of systems. Like for the first time, we have actually proved, and that is Alexei's work, he's sitting here, his master's thesis actually has proven that Apache Flink is failure transparent. And so we have like, formal definition, proof, and so on, formalization of the system. So this is within the Portals project, so you can see some papers here as well. And here are some references if you're interested in these things. Yeah, so to conclude, so Scala 3 and capture checking really provides a new way to program with effects, right? And we have this effect polymorphism, which is so powerful because it lets us reuse huge APIs, right? Collection APIs, for instance. And Gears is an experimental concurrency library, which uses, on the one hand, this new runtime support for lightweight threads that we have on JDK 21 and also on Scala native support for delimited continuations, right? And then also Scala 3 contextual abstractions, like context parameters and so on. And then capture checking is really cool because it can actually be used to enforce effect safety. Yeah, that's all I had. Thank you.